So this is the final part in PIC game programming, and it covers the gameplay. So in the constants, there's just this constant to add, and this is just saying how many times the correct LED should flash in the gameplay when a player gets the selection wrong and it ends the game. And for the RAM variables, I'm going to add another couple of temporary variables because in the gameplay things get a bit more complicated and how to move things around from the W register. And then there's this register here, LED compare. So when the gameplay, when the players pressing the sequence that they believe is the right sequence, I need to take what was the actual sequence value and what they've selected and compare them. So this is to hold one of those values within it. And then finally for the RAM registers, there's the sequence values. So this is an area of RAM which goes from 40 hex and it consumes 16 addresses, and this is where it stores and compares back the sequence value for the gameplay. And there's a little bit of initialization code to add, and this comes from the last part. So in the last part, the user can select the level, but when the system boots up and the level button hasn't been pressed yet, the actual number of sequences for the first level hasn't been set, so you need to set it manually in the initialization code. So you need 3 functions to support the gameplay, and the first one is here, sequence add. So the actual game is, each time it goes around a set of sequences, it adds a sequence to it, and then the next sequence it'll add another sequence to it. So this is just to add a sequence to the list of sequences that already exist. First thing it does is it gets a random value. It then stores it in a temporary area because it needs to do something with the W register sort of meanwhile. And it needs the W register to set up the address of where to store the sequence. So it gets the base address of the sequences in RAM. It adds the offset that we're currently at, which is sequence count, and the first time round this will be 0, so it'll add it to the first memory address of sequences. And it takes that address and it puts into the indirect addressing address register, and then it recalls the random value from memory that it stored earlier. And the reason it doesn't call this get_round down here rather than storing it in a temporary register then restoring is because we make a call to get_round. When we make a call to get_round, it could be affecting this FSR indirect addressing register, in which case it would the call being made here would upset the address that we want to store the actual value into. And then this stores the value that we've just recalled, which is the random value, into the sequences at the sequence where we want it. And then we increment the sequence count so that next time round it adds the next sequence to the next value in RAM where the sequences are stored. So the next function which is required is sequence play. So when playing the game, it goes around a series of things. So first of all, we're asked to add a value to the sequence because otherwise there'd be nothing in the sequence queue to play. And then it plays, the actual processor plays the sequence of LEDs with beeps if the sound is turned on. And then finally, which will be the next function, it needs to get the user's feedback as to what the beep sequence is, and it compares it and decides whether the player has lost or won. So to play a sequence, first of all use a temporary register, and this is to count my way through the sequence from the first sequence value to whatever the current end sequence value is. Then I set up the LEDs just to be a pause and no LEDs displayed, and I display that. So this pause flag just stops the LEDs from animating if there's a current animation going on, and it just updates the LEDs with nothing, and then it does a very short pause so that the user sees a delay, because the processor can do things a lot quicker than the user. So Just need to let the user know there's a gap here. Then in order to get the next sequence value to play back, so first of all, start off at the first sequence value, get the address of the sequences in RAM, and then I add this temp free value which I set up at the very top here, which is my count into the sequence values. And then I put that into the indirect addressing address and read the address into the W register on this line. And I store the value that I read back into temp4, because W register gets used for all the operations that you do when you use an assembly. So if you want to use that value again, it's best to store it in a temp4 register directly in RAM, rather than next time you want to use it going through the indirect addressing again, which is these 4 lines of code. You just need to read temp4 instead. And then I get so when the user sets levels, they can set a level 1 to 4 for how many things to remember, and also they can set a level 1 to 4 for the number of simultaneous LEDs which can be lit at any one time. So I'm getting that value, the simultaneous level, which can be, it'll be a value of 0 to 3 because it's a 0 offset, but it maps onto the values 1 to 4 for the simultaneous level. And I just store that into temp2. So I'm going to use that to count how many times I should be setting an LED on, depending on how many simultaneous LEDs can be set on. And I'm incrementing the value by 1, so it changes it from a value of 0 to 3 to 1 to 4, which I can count through. And I'm also using a third temporary value, which is to construct a beep note from. So when it plays, if the sound's turned on, and it's going, each LED has its own frequency, and so it will calculate which frequency it should be playing in this temp1 value as we go through. Now I'm about to access temp4, which is the current sequence I want to display, and each sequence is a random set of values in a byte, so that's 8 bits in the byte. So if you just take a look at this number here, this is 8 bits, so this is effectively what temp4 looks like, only each bit in this in temp4 is completely random. It's not the value that you see here. But what I'm doing in this particular thing is loading into the W register just the bottom 2 bits, because I'm about to just mask those out of temp4, so I'm only going to get the bottom 2 bits out of temp4. And I'm going to use that as a definition as to which LED to light. So if you take two bottom bits, the first one is 1 and then 2, and they can have a combination of anything from 0 to value 3. So that's actually 4 values: 0, 1, 2 and 3. That can define which LED we want to light, because there's only 4 LEDs. So each 2 bits of temp4 we can use to define an LED, and that's really handy because there's 4 lots of 2 bits in temp4. So as we can light up to 4 LEDs, and each 2 bits defines an LED, we've got 4 sets of 2 bits, so we can actually define up to 4 LEDs being lit per sequence. And that's what will happen down here. So I'll go through and try and explain that. So here I'm loading up the bottom 2 bits of into the W register, and I'm using the AND logical operator to mask out those 2 bits from temp4, which is the current sequence. So this is now using, I'm going to make an operation on temp1, which is what I'm using to store the beep frequency. So whatever the value of the LED is, from 0 to 3, I'm going to put into the frequency of the beep that I want to use. And then I'm going to look up which LED I want to actually light. So I've got a value from 0 to 3, but that's no good to me because I need to convert it into which bit I need to set in the LEDs to actually light the LED. So if I take this, if I take the value that I've got, which can be from 0 to 3, and what I'm doing is adding this, which is the address of the LED lookup for rotating LEDs clockwise, which defines each LED in sequence, but the offset of the value I've got from 0 to 3 in there will actually light one of the 4 LEDs. Then I read the EEPROM value, and that will give me the actual bit that I need to light whichever LED I need to light. And then I add the definition of that LED to which I've just read from EEPROM to the actual current LED state. So and I'm using an OR, so that sets the bit that I want to set for that particular LED. And then I'm rotating right the value of my sequence by 2 bits, which gets rid of the definition I've just lit, and then it will move the next definition I want to light into the bottom 2 bits of temp 4. So where I've got here, I'm decrementing temp 2, which was the number of simultaneous LEDs I want to light for whatever value is set for the simultaneous level, and it'll go around this loop up here and light as many LEDs as I need for the simultaneous. Now sometimes random numbers might be the same, so if it's if the random value of 2 is used twice, then it will just set that LED twice, and one of the LEDs will be blank because one of them won't get lit. So it's literally any value from one LED being lit, because if they're all of these bits are the same value, all these pairs of bits are the same value, then it's only going to light that one LED which they will define, which is going to be the same. But it goes around this loop and lights as many bits as it needs for a simultaneous level, and that's a little bit complicated, but that's how that works. And it'll only use the highest frequency, so the beep it uses will be the highest frequency of the LED to actually use, because it's ORing the value on top of each other each time. So after it's decided to light the LED for that particular sequence, it will take the value in temp 1, which is the beep frequency that we want, and it will add an offset into the frequency table, so that it's not a really low frequency it's playing, it's going to be one of the higher frequencies that we want to play. And it sets the beep period, which is the high nibble. It sets it to a short beep, and then it calls start beep to start the beep playing. Now because up here I loaded the value directly into the LED state register, an interrupt will take that value and display that LED value, so I don't have to worry about calling anything to display the LEDs, because it will automatically get displayed from the interrupt when it sees the value in LED state. But what I want to do after it's done a short pause, so between each sequence it's displaying, it's going to do this short pause here. I want to also make sure, because it's playing back and there's no human interaction, that the game doesn't time out on its sleep value and go to sleep whilst it's playing back these beeps and LED sequences. So I just reset that to the maximum sleep timeout, so it can start counting that down and not fall to sleep halfway through. And then because I'm counting how many sets are in this sequence in temp 3, I point to the next value we want to display for the sequence. I move it into the W value as well, because what I want to do is I want to check and see if we're at the maximum sequence count for what we're currently playing. And so doing an exclusive OR with what's in temp 3 with the maximum count we want to go to, if that matches, it will set the 0 flag, and if it's still got more to play, it'll go around this loop up to the very top again, and it'll go through and play the next sequence, and it will just play all the sequences it needs to play for this particular set of sequences. And then at the very end, I want to make sure that no LEDs are left lit from playing back the sequence, so I just clear the LED state flag, and then that leaves it clean. So the last procedure that's required is this sequence repeat, and what this does is it allows the user to press the sequence of buttons which are required, and it compares them with the sequence it played and decides whether the player's got them right or wrong. And it's very similar to the previous function. So again, we're going to use temp3 as a sequence pointer, which are used in the previous function, and going to have reset the player timeout. So each time a player presses a button or has to press a button, they get a timeout period which they're allowed to take so much time before pressing the button. If they take too long, then they'll lose the game. And also, I don't want the device to go to sleep, so again, I'm going to, because this process can take a while, I'm going to make sure that each iteration through this loop reset the sleep timeout so that the device doesn't go to sleep. And the LED compare register I'll reset as well. So the LED compare register is what I'm going to use to compare what should be pressed by the user with what the user actually presses. So first of all, I'm going to get the value which the game is going to expect the user to press from the sequences which is supposed to be, and this is going to be very similar to the previous function. So first of all, I'm going to get the sequence address in RAM. I'm going to add the offset that we're currently at. So first time it will be 0, then next time around it'll be 1, 2, 3. That will point to which sequence we're currently looking at. So they're going to put that in the indirect address register, and then I'm going to read from that address the actual sequence that we're looking at, the value. And like before, I'm going to put it into the temporary register temp4 because I'm going to use that again later. And I'm going to load the number of simultaneous LEDs into the W register and store that in temp2 so we can count through that, increment it to, so it goes from 0 offset to of 0 to 3 up to an offset of 1 to 4. I'm going to clear the temporary register 1 because I'm going to construct again the beat value in temp1. So this is all like we did in the previous function. And again, I'm going to just take the bottom 2 bits at any one time. So I'm going to use the 2 bits at a time to define an LED value of one of the 4 LEDs. I'm going to add that with temp4. So I'm just going to take the bottom 2 bits off of temp4. For the sound, I'm going to OR that with temp1. So I'm going to build up whichever beep offset we want in temp1. I'm going to add the address in EEPROM of the LED rotation animation, so I can get a value of the LED that I actually want to display from that table. And I'm going to read that value from the EEPROM, and I'm going to then OR that onto the current LED compare this time. So previously we ORed it with LED the LED being displayed to display it directly, but we don't want to display it this time because we want to see what the user presses. So now I'm building up this LED compare register rather than the LED display register, and going to get the next 2 bits from the temp4 register, which is the current sequence, and I'm going to go around this loop and build up as many as for LEDs as we require for the current sequence level that we have set, which might be anything from 1 to 4. So we've got this key log here, and that's going to be used to log which keys are being pressed for a particular sequence. So I'm clearing it at this point because I want to start off with no keys being registered, and I wait for the user to press a key. So because when it comes in here, the user's not going to be pressing the key. So if I didn't wait for the user to first press a key, it would just fly through this and go on and not register what I need them to register, which is what key presses are. So it waits for the user to press the first key, and then it waits for the user to release all keys. So while the user's got a key pressed down, they can actually, if they've got simultaneous LEDs being lit, they can actually press all the keys for the lit LEDs that they expect to see. Or if it's just one LED, then all they'll have is one key pressed down any time. So it waits for all the keys to be up. So that will be the user's turn as to what the user thinks the key press should be for the LEDs, and that will get logged in key log. And then I move the key log register into the W register, and I mask out each of the LEDs, the LED bits, because all the keys are on the same I/O ports as the LEDs and they corresponding keys to each LED. It's actually very easy to compare them because the values are going to be the same. So for a particular LED which is being lit, that key, the same bit on the bit being read for the key, will be identical. So all I have to do is compare what I expect the LEDs to be lit with the actual key log directly, and if it's a 0, then that means they match. If it's not 0, then it means they don't match. So if what the user pressed wasn't what was expected, then it forces an error state by clearing the player timeout count, and if it does that, effectively the player times out and it forces the error state. So it's just like a convenient way of making the user lose when they press the incorrect keys. And then it'll check the player timeout to see if the player has timed out, and if they have, then it will come out of the function. So at this point, the player could have timed out for two reasons. So it could have either that the player did actually time out and the count counted down to 0, or it might be that the count was forced to 0 here, where the player didn't press the right key, and so therefore they were forced out of the function. Otherwise, it will skip over this. It'll increment to the next value in the sequence, and then check to see if it's the last value in the sequence, if it's got to the end of the list, and if it has, it will just come out of the function. Otherwise, it'll go around and do the next element in the sequence up here, and it'll just keep going around there until it's got through all the sequences, or until a player's pressed the wrong key, or until the player's timed out. So to complete the code, I come back up to the main loop of the application. So in the last video we did set in the settings for the user. So when they decide to start a game, the mode will be game mode, and it will call this mode game function, which you can find down here. So this is what finally brings it all together, and how to play the game. So initially, when come into game mode, sub game mode to be 0, which is effectively initialize this game mode. So that will come down to here, and it sets the next game mode that we want to be in when we come back through this loop again. So we want the next one to be gameplay. But whilst we're in initialization, we're going to turn off any animations of the LEDs, so make sure there's no LED animation occurring when we start the game, and reset the sequence count to 0. So we'll start off with sequence 0, it'll add 1, it'll be sequence 1, then 2 and 3 and 4, and it'll go on from there. And it just makes sure that the player timeout flag is cleared, so that when we go into the game, it doesn't immediately time out the player. And then so we go to the end of this function, and then when we come back round again next time round the loop, we come into this function, we'll be coming down to here because we set that up here when we initialize to come into this point of the function next time round. So each sequence of the game which is added will go through this process which we're about to go through. It'll check to see if the player's timed out. If they have, it goes to the game lose function, part of the function. I'll go through the game lose and game win part of the function at the end. It checks to see if the player has actually correctly guessed all the sequences for the game, and it's come to the end of the level. And if they have, so it does a comparison with what the maximum sequence should be with what the current sequence is. And if it'll be 0, the 0 flag will be set if they've come to the end of the sequence, and it will show them a game win when they win the game and have correctly repeated the full sequence. Otherwise, it does a quick pause before going into the next set of sequences, First thing it needs to do is add a sequence. So first time around here it would be 0 sequences. Then each time around this loop it will be add an extra sequence until it gets up to the maximum sequence or the play loses. After it's added the sequence, it will play the sequence to the player, and then it will get them to repeat the sequence back and decide whether or not they've correctly guessed the sequence. It checks the player timeout count, because remember there's two reasons why it might be 0 at this point. It might be that the player's timed out and therefore they lose because they've timed out, or it might be in the sequence repeat function the player timeout can be set, or the actual count can be cleared when the player actually does an incorrect guess, and therefore it's forcing the player to a losing state. And so if that happens, if either of those cases happen, it goes to this lose game function, the part of the function. So that's the gameplay part of the function. Then there's just the two parts which we covered in that, which was the first one is if the player wins, it'll play an LED sequence of animation for a win. So there's a certain animation it'll play for a win, and there's also a certain tune it'll play for a win. And after it's done that, it'll tell it to go to sleep. So it'll go down to this bit of the function at the bottom here. It'll do a long pause, so it gets a chance to do the animation and play the tune. And then it'll set the mode to sleep, and it'll clear all key presses. So it'll automatically force it to go to sleep. Or, apart from a win, another way out of here is to go through the lose path, in which case it does a similar thing, but it'll play a lose tune, and then it'll flash the LED sequence that the player should have pressed 5 times. So it loads that value 5, which is the lose loop count, into temp2, so it can count down from there. And it also sets a flag in the LED state to say, well, we don't want any animations happening whilst we're doing this, whilst we're showing the player what buttons they should have pressed. And so it puts that into the LED state. It does a short pause with no LEDs lit, so that so this is part of the flashing. So first of all, it displays no LEDs, and then it moves the LED compare into the LED state. Because this LED compare is only ever used in the gameplay, and it will be the last value which was compared against what the user pressed. This will be the actual correct value which they should have pressed, and so it puts that into the LED state. Does a short pause again. It decrements the counter, and it goes through this lose loop. So it'll then display nothing for a short period, and then display the LED compare again for a short period. And it'll do that 5 times just to flash to the user what they should have pressed. And then after it's finished doing that, it'll do an animation of an LED lose sequence, because it's already playing a tune from the start up here. So it's now playing the tune and doing the lose animation sequence after flashing the correct LEDs that they should have pressed. Then it will naturally fall into this long pause and go into sleep mode and clear key presses, and that completes all of the code for the game. So I've loaded the completed game code into this PIC microcontroller, put it in circuit, and it switches on immediately. And I can switch the sound on. I can set the level to level 2, set the sequence count to level 2, start game, and it'll play, and it should play with up to 2 LEDs lit at any one time. And it adds a extra bit of complexity. Extra bit of complexity, having to have pressed more than one button at any one time for a game. And that's the completed code.